In 1981, the U.S. Air Force identified a requirement for an Advanced Tactical Fighter ATF to replace the F-15 Eagle and F-16 Fighting Falcon. Codenamed Senior Sky, this air superiority fighter program was influenced by emerging worldwide threats, including new developments in Soviet air defense systems and the proliferation of the Su-27 Flanker and MiG-29 Fulcrum class of fighter aircraft. It would take advantage of the new technologies in fighter design on the horizon, including composite materials, lightweight alloys, advanced flight control systems, more powerful propulsion systems, and most importantly, stealth technology. In 1983, the ATF concept development team became the System Program Office SPO and managed the program at Wright-Patterson Air Force Base. The demonstration and validation request for proposals RFP was issued in September 1985, with requirements placing strong emphasis on stealth and super cruise. Of the 7 bidding companies, Lockheed and Northrop were selected on 31 October 1986. Lockheed teamed with Boeing and General Dynamics, while Northrop teamed with McDonnell Douglas, and the two contractor teams undertook a 50-month demonstration and validation phase, culminating in the flight test of 2 technology demonstrator prototypes, the IF-22 and the IF-23, respectively. Concurrently, Pratt & Whitney and General Electric were awarded contracts to develop the YF-119 and YF-120, respectively, for the ATF engine competition. Demonstration and validation was focused on risk reduction and technology development plans over specific aircraft designs. Contractors made extensive use of analytical and empirical methods, including computational fluid dynamics, wind tunnel testing, and radar cross-section calculations and pole testing. The Lockheed team would conduct nearly 18,000 hours of wind tunnel testing. Avionics development was marked by extensive testing and prototyping, and supported by ground and flying laboratories. During demonstration and validation, the SPO used the results of performance and cost trade studies conducted by contractor teams to adjust ATF requirements and delete ones that were significant weight and cost drivers while having marginal value. The short takeoff and landing STOL requirement were relaxed in order to delete thrust reversers, saving substantial weight. As avionics was a major cost driver, side-looking radars were deleted, and the dedicated infrared search and trackers system was downgraded from multicolor to single color and then deleted as well. However, space and cooling provisions were retained to allow for future addition of these components. The ejection seat requirement was downgraded from a fresh design to the existing McDonnell Douglas ACES 2. Despite efforts by the contractor teams to rein in weight, the takeoff gross weight estimate was increased from 22,700 kg to 27,200 kg, resulting in engine thrust requirement increasing from 133 kN to 156 kN class. Each team produced 2 prototype air vehicles for demonstration and validation, one for each of the 2 engine options. The IF-22 had its maiden flight on 29 September 1990, and in-flight tests achieved up to Mach 1.58 in Super Cruise. After the DEM-VAL flight test of the prototypes, on 23 April 1991, Secretary of the USAF Donald Rice announced the Lockheed team and Pratt & Whitney as the winners of the ATF and engine competitions. The IF-23 design was considered stealthier and faster, while the IF-22, with its thrust vectoring nozzles, was more maneuverable as well as less expensive and risky. The aviation press speculated that the Lockheed team's design was also more adaptable to the U.S. Navy's Navalized Advanced Tactical Fighter NATF, but by 1991, the Navy had abandoned NATF. The Lockheed Martin F-22 Raptor is a single-seat, twin-engine, all-weather stealth tactical fighter aircraft developed for the United States Air Force USAF. The result of the USAF's Advanced Tactical Fighter ATF program, the aircraft was designed primarily as an air superiority fighter, but also has ground attack, electronic warfare, and signal intelligence capabilities. The prime contractor, Lockheed Martin, built most of the F-22's airframe and weapons systems and conducted final assembly, while Boeing provided the wings, aft fuselage, avionics integration, and training systems. The aircraft was variously designated F-22 and FA-22 before it formally entered service in December 2005 as the F-22A. Despite its protracted development and various operational issues, USAF officials consider the F-22 a critical component of the service's tactical air power. Its combination of stealth, aerodynamic performance, and avionics systems enable unprecedented air combat capabilities. Service officials had originally planned to buy a total of 750 ATFs. In 2009, the program was cut to 187 operational production aircraft due to high costs, a lack of clear air-to-air missions due to delays in Russian and Chinese fighter programs, a ban on exports, and development of the more versatile F-35. The last F-22 was delivered in 2012. The F-22 cannot be exported under U.S. federal law to protect its stealth technology and classified features. Customers for U.S. fighters are acquiring earlier designs such as the F-15 Eagle and F-16 Fighting Falcon or the newer F-35 Lightning II, which contains technology from the F-22 but was designed to be cheaper, more flexible, and available for export. In September 2006, Congress upheld the ban on foreign F-22 sales. Despite the ban, the 2010 Defense Authorization Bill included provisions requiring the Department of Defense to prepare a report on the costs and feasibility for an F-22 export variant and another report on the effect of F-22 export sales on U.S. aerospace industry. Some Australian politicians and defense commentators proposed that Australia should attempt to purchase F-22s instead of the planned F-35s, citing the F-22's known capabilities and F-35's delays and developmental uncertainties. However, the Royal Australian Air Force RAF determined that the F-22 was unable to perform the F-35's strike and close air support roles. The Japanese government also showed interest in the F-22 for its replacement fighter program. The Japan Air Self-Defense Force JASDF would reportedly require fewer fighters for its mission if it obtained the F-22, thus reducing engineering and staffing costs. However, in 2009 it was reported that acquiring the F-22 would require increases to the Japanese government's defense budget beyond the historical 1% of its GDP. With the end of F-22 production, Japan chose the F-35 in December 2011. Israel also expressed interest, but eventually chose the F-35 because of the F-22's price and unavailability. The F-22 Raptor is a fifth-generation fighter that is considered fourth-generation in stealth aircraft technology by the USAF. It is the first operational aircraft to combine super cruise, super maneuverability, stealth, and sensor fusion in a single weapons platform. The F-22 has 4 empennage surfaces, retractable tricycle landing gear, and clipped delta wings, with reverse trailing edge sweep and leading edge extensions running to the upper outboard corner of the inlets. Flight control surfaces include leading edge flaps, flaprons, ailerons, rudders on the canted vertical stabilizers, and all moving horizontal tail stabilators. For speed brake function, the ailerons deflect up, flaprons down, and rudders outwards to increase drag. The aircraft's dual Pratt & Whitney F119PW100 augmented turbofan engines are closely spaced and incorporate pitch-axis thrust vectoring nozzles with a range of plus or minus 20 degrees. Each engine has maximum thrust in the 156 kN class. The F-22's thrust-to-weight ratio at typical combat weight is nearly at unity in maximum military power and 1.25 in full afterburner. Maximum speed without external stores is approximately Mach 1.8 at military power and greater than Mach 2 with afterburners. The F-22's high cruise speed and operating altitude over prior fighters improve the effectiveness of its sensors and weapon systems and increase survivability against ground defenses, such as surface-to-air missiles. The ability to supercruise or sustain supersonic flight without using afterburners allows it to intercept targets which subsonic aircraft would lack the speed to pursue, and afterburner-dependent aircraft would lack the fuel to reach. The F-22's thrust and aerodynamics enable regular combat speeds of Mach 1.5 at 50,000 feet. The use of internal weapons bays permits the aircraft to maintain comparatively higher performance over most other combat-configured fighters due to a lack of parasitic drag from external stores. The airplane's structure contains a significant amount of high-strength materials to withstand stress and heat of sustained supersonic flight. Respectively, titanium alloys and composites comprise 39% and 24% of the structural weight. The F-22's aerodynamics, relaxed stability, and powerful thrust vectoring engines give it excellent maneuverability and energy potential across its flight envelope. The airplane has excellent high alpha characteristics, capable of flying at trimmed alpha of over 60 degrees, while maintaining roll control and performing maneuvers, such as the Herbst maneuver and Pugachev's Cobra. The flight control system and full authority digital engine control FADEC make the aircraft highly departure resistant and controllable, thus giving the pilot carefree handling. The F-22 Raptor has an integrated avionics system where through sensor fusion, data from the radar, other sensors, and external systems are filtered and combined into a common view, thus enhancing the pilot's situational awareness and reducing workload. Key systems include Sanders General Electric AN ALR-94 electronic warfare system, Lockheed Martin AN R-56 infrared and ultraviolet missile launch detector MLD, Westinghouse Texas Instruments AN APG-77 active electronically scanned array ESA radar, and TRW Communication Navigation Identification CNI suite. The MLD uses 6 sensors to provide full spherical infrared coverage. Among the most technically complex equipment on the airplane is the ALR-94 system, a passive radar detector with more than 30 antennas blended into the wings and fuselage for all-round radar, warning receiver RWR coverage. Its range 250+ nautical miles exceeds the radar's and can cue radar emissions to be confined to a narrow beam down to 2 degrees by 2 degrees in azimuth and elevation to increase stealth. Depending on the detected threat, the defensive systems can prompt the pilot to release countermeasures such as flares or chaff. The ALR-94 can be used as a passive detection system capable of searching targets and providing enough information for a radar lock-on. Tactical communication between F-22s is performed using the Directional Inter-Intraflight Data Link IFDL. The APG-77 radar has a low observable active aperture electronically scanned array that can track multiple targets under any weather conditions. Radar emissions can also be focused to overload enemy sensors as an electronic attack capability. The radar changes frequencies more than 1,000 times per second to lower interception probability and has an estimated range of 241 kilometers against a 1 meter square target and 400 kilometers or more in narrow beams. F-22s from Lot 5 and on are equipped with the APG-77V1, which provides air-to-ground functionality through synthetic aperture radar mapping and various strike modes. Radar and CNI information are processed by 2 Hughes Common Integrated Processor SIPs, each capable of processing up to 10.5 billion instructions per second. The aircraft has also been upgraded to incorporate an automatic ground collision avoidance system GCAS. The F-22's ability to operate close to the battlefield gives the aircraft threat detection and identification capability comparative with the RC-135 rivet joint and the ability to function as a mini AWACS, though its radar is less powerful than those of dedicated platforms. This allows the F-22 to rapidly designate targets for allies and coordinate friendly aircraft. Data can be transferred to other aircraft via Link 16 using the MIDS-J radio. The IEE 1394B bus developed for the F-22 was derived from the commercial IEE 1394 Firewire bus system. In 2007, F-22's radar was tested as a wireless data transceiver, transmitting data at 548 megabits per second and receiving at gigabit speed, far faster than the Link 16 system. The F-22's software has some 1.7 million lines of code, the majority involving processing radar data. Former Secretary of the USAF Michael Wynn blamed the use of the Department of Defense's ADA for cost overruns and delays on many military projects, including the F-22. The integrated nature of the avionics has also made upgrades challenging. Consequently, open system architecture for the aircraft is currently planned in order to facilitate future upgrades. The F-22 has 3 internal weapons bays, a large main bay on the bottom of the fuselage, and 2 smaller bays on the sides of the fuselage, aft of the engine intakes. The main bay is split along the centerline and can accommodate 6 LAU-142A launchers for beyond visual range missiles, and each side bay has a LAU-141A launcher for short-range missiles. 4 of the launchers in the main bay can be replaced with 2 bomb racks that can each carry 1 450 kg or 4 110 kg bombs. Carrying armaments internally maintains the aircraft's stealth and minimizes additional drag. Missile launches require the bay doors to be open for less than a second, during which pneumatic or hydraulic arms push missiles clear of the aircraft. This is to reduce vulnerability to detection and to deploy missiles during high-speed flight. The F-22 can carry air-to-surface weapons such as bombs with JDAM guidance and the small-diameter bomb, but cannot self-designate for laser-guided weapons. Internal air-to-surface ordnance is limited to 910 kilograms. An internally mounted M61A2 Vulcan 20mm rotary cannon is embedded in the airplane's right wing root, with the muzzle covered by a retractable door to maintain stealth. The radar projection of the cannon fire's path is displayed on the pilot's head-up display. The F-22's high cruise speed and altitude increased the effective ranges of its munitions, with the aircraft having 50% greater employment range for the AIM-120 AMRAAM and twice the effective range for JDAMs than prior platforms. In testing, an F-22 dropped a GBU-32 JDAM from 15,000 meter while cruising at Mach 1.5, striking a moving target 39 kilometers away. While the F-22 typically carries weapons internally, the wings include 4 hardpoints, each rated to handle 2,300 kilograms. Each hardpoint can accommodate a pylon that can carry a detachable 2,270 liters external fuel tank or a launcher holding 2 air-to-air missiles. The 2 inboard hardpoints are plumbed for external fuel tanks. The use of external stores degrades the aircraft's stealth and kinematic performance. After releasing stores, the external attachments can be jettisoned to restore those characteristics. A stealthy ordnance pod and pylon was being developed to carry additional weapons in the mid-2000s. The F-22 was designed to be highly difficult to detect and track by radar. Measures to reduce radar cross-section RCS include airframe shaping such as alignment of edges, fixed geometry serpentine inlets and curved vanes that prevent line of sight of the engine faces and turbines from any exterior view, use of radar-absorbent material RAM, and attention to detail, such as hinges and pilot helmets, that could provide a radar return. The F-22 was also designed to have decreased radio emissions, infrared signature and acoustic signature, as well as reduced visibility to the naked eye. There were mainly 4 variants of F-22 Raptor that were developed in US till date. The F-22A pre-production technology demonstrator for Advanced Tactical Fighter ATF demonstration validation phase 2 were built. The F-22A single-seat production version was designated FA-22A in early 2000s. The F-22B planned 2-seat variant, cancelled in 1996 to save development costs with test aircraft orders, converted to F-22A. The naval F-22 variant, a planned carrier-borne variant of the F-22 with variable sweep wings for the U.S. Navy's Navy Advanced Tactical Fighter (NATF) program to replace the F-14 Tomcat. The program was cancelled in 1991. The aircraft's flat thrust vectoring nozzles reduce infrared emissions of the exhaust plume to mitigate the threat of infrared homing heat-seeking surface-to-air or air-to-air missiles. Additional measures to reduce the infrared signature include special topcoat and active cooling of leading edges to manage the heat buildup from supersonic flight. Compared to previous stealth designs like the F-117, the F-22 is less reliant on RAM, which are maintenance-intensive and susceptible to adverse weather conditions. Unlike the B-2, which requires climate-controlled hangars, the F-22 can undergo repairs on the flight line or in a normal hangar. The F-22 has a signature assessment system which delivers warnings when the radar signature is degraded and necessitates repair. While the F-22's exact RCS is classified, in 2009 Lockheed Martin released information indicating that from certain angles the airplane has an RCS of 0.0001 meters square, equivalent to the radar reflection of a steel marble. The aircraft can mount a Lundberg lens reflector to mask its RCS. Effectively maintaining the stealth features can decrease the F-22's mission-capable rate to 60–70%. The effectiveness of the stealth characteristics is difficult to gauge. The RCS value is a restrictive measurement of the aircraft's frontal or side area from the perspective of a static radar. When an aircraft maneuvers, it exposes a completely different set of angles and surface area, potentially increasing radar observability. Furthermore, the F-22's stealth contouring and radar-absorbent materials are chiefly effective against high-frequency radars, usually found on other aircraft. The effects of Rayleigh scattering and resonance mean that low-frequency radars such as weather radars and early warning radars are more likely to detect the F-22 due to its physical size. However, such radars are also conspicuous, susceptible to clutter, and have low precision. Additionally, while faint or fleeting radar contacts make defenders aware that a stealth aircraft is present, reliably vectoring interception to attack the aircraft is much more challenging. According to the USAF, an F-22 surprised an Iranian F-4 Phantom II that was attempting to intercept an American UAV, despite Iran's assertion of having military VHF radar coverage over the Persian Gulf.